Until now, we have talked about the branch if equal and branch if not equal, these two conditional decision-making operations. And the condition is equality. Basically, we judge whether two source operands are equal or not. And based on that equality, conclusion we achieved to decide whether we need to branch to certain targeted instructions or not. However, the condition for making those kind of conditionally decision making is not always be equality. For example, I still want to judge whether certain two instructions, whether certain two operands satisfy the condition that whether S0 is larger than S1. If S0 larger than S1, I will branch to certain instruction L. If S0 not less than S1, I will not branch to. Maybe I using the word is easier to represent is a neater way, right? So basically, I can try to say whether whether S1 is larger than S0. If it is larger, I will branch to the certain instruction with the label L. I can also try to judge whether S1 is larger or equal to S2 or S0. If it satisfies this condition, I will branch to the instruction with label L. And I also can tell whether S1 is larger than S0. If S1 larger than 0, I will branch, otherwise will not. I also can tell whether S1 is larger or equal to S0. If this condition satisfied, I will branch, right? So basically, you can see beside branch if equal, branch not equal, I also can use in condition less or equal than, larger or equal than as a condition. However, I want to say is all those instructions we consider as a pseudo instruction. Everyone still remember what means pseudo instruction? Pseudo instruction means the assembler of the computer understand the meaning of those assembly language. However, those assembly instructions or those operations will not be included in the official instruction set. So in order to explain that in more detail from the operation perspective, basically assembler will translate those pseudo instruction into one or set of the corresponding regular official instruction in order to represent the meaning appropriately. Say one more time, assembler understand those instructions, but those instructions are not included in the official instruction set. Alright, so now the question is, if assembler receive those kind of pseudo instruction, how they can translate those pseudo instruction into the set of official instructions in order to represent them appropriately. In order to achieve this goal, we introduce another instruction which is included in the instruction set, which called set on less than. Set on less than can be represented in a standard way as the following: set on less than followed by a destination operand T0 and then followed by two source operand S0 and S1. And what this instruction try to represent is, if S0 less than S1, then T0 will be equal to 1, otherwise T0 will be 0. say one more time, if the first source operand is less than the second source operand, then the destination will equal to 0. Otherwise, the destination operand will be, I'm sorry, so let me say one more time. If as the first source operand is less than the second source operand, then the destination operand will be equal to 1. Otherwise, this destination operand will be equal to 0. And now from here, actually, before we move forward to talk about how to represent branch if less than, branch if larger than, and so on, by using the branch if equal, branch not equal, and set and less than, let's focus on the set and less than itself for a little bit. So here, actually, I already represented in the slides, we can see the set and less than will represent using R format for the machine language, or we call it for the instructions. The reason is obviously, right? Because it's assembly language using a standard R format assembly language representation, operation, destination to source. Therefore, if you try to represent R format or if you try to represent this instruction by using R format, you're supposed to be able to understand how I can fit in those individual information into the individual segment in the R format by using our understanding of the R format 6 segments. So first segment supposed to be 0 because as long as this instruction is R format, I will using 0 to represent operation code. The last segment, which is function code, I using 42 to represent this operation set and less than. And then the shift amount, which is in this segment, will be 0 because that instruction is not a shift left or shift right logic. And then this segment will represent RS, which is the first source operand, which is at 0 here. Therefore, I'm using 16. And then this segment will represent RT, which is second source operand, which is S1. And then this segment will use to contain the information of the destination operand, which is T0 in this instruction, and T0, the index will be 8. Therefore, I can represent this assembly language related to set and less than by using this corresponding sequence of decimal numbers. And you require to represent the R format of the instruction properly by using the sequence of binary number, which is translated from this sequence of binary decimal number based on the understanding of how many bits assigned to the individual segments. And there is an alternative version of the set and less than. For example, if one of the source operand is a constant, instead of using set and less than, I using set and less than immediate. If all the source operands are negative, I will using set and less than unsigned to replace set and less than. And if the second source operand is a positive number or non-zero number or non-zero constant, and the fourth source operand is also non-negative, then I will represent the set and less than by using the set and less than immediate unsigned. Again, you are not have to do so, but you should be able to understand there is a different alternate version of the set and less than. Immediate means the second operand is constant. Unsigned means the both source operand are non-negative. Immediate unsigned means second operand a non-negative constant and first source operand a non-negative variable. This is very important because sometimes if you not pay attention enough to the operation, you might have some mistake. Just this example give you an example to show how important to pay attention to the operation representation, whether that is a set and less than, or set and less than unsigned, or set and less than immediate, or set and less than immediate unsigned. For example, if I know S0 which is a first source operand, is represented as this way, and S1, which is second source operand, represents this way, and I will implement the set down less than, and then followed by destination T0, followed by the first source operand S1, second source operand first source operand S0, second source operand S1. If I using set down less than, means I assume the source operand can be negative. Therefore, the S0 will be the negative number, right? Because the sign bit is 1. But because of that, and also we know S1 is a positive number because the sign bit is 0. Therefore, I know S0 is less than S1. Because of that, T0 will assign with 1, which is demonstrated as here. Similarly, if I using the operation as a set down less than unsigned, basically I assume S0 and S1 are both unsigned number, then all of those bits will only represent value bits instead of sign bit. Then S0 will be a positive number which is much larger than S1. Because of that, T0 will be assigned as 0 instead of 1. And here demonstrated here. Therefore, you can see the destination operand T0 will be concluded as a different value once 1, once 0, based on the difference of the operation, whether it is set down less than and set down less than unsigned. Again, this is just to give you an example to emphasize how important the operation is. Now, we go back to our original question, how I can using the combination of set down less than, branch equal, or branch not equal to represent the equivalent operation of the pseudo instructions, branch larger than, branch less than, equal, less or equal than, branch greater than, or branch if greater or equal than. So I just demonstrate the first one, how I can represent branch less than this pseudo instruction by using the combination of these instructions. So I want you to pause here to think a little bit and then continue with the slides. I can represent branch less than by using set on less than and branch equal. You can see if I want to represent here is if S1 less than S2, then I will branch to the instruction with a certain label. And let's look at here. If S1 less than S2 satisfy this condition, then I will assign the value of this assembly, register AT. AT is one of the general purpose register, which called the assembler temporary register. And we will introduce the detail of this register in more details. But here you just say this is one destination operand. Then what I mean is if S1 less than S2, this destination operand will be equal to 1. Okay? So here the second instruction to say is if this general purpose register is not equal to 0, I will branch to the instruction with label. Then, because S1 is less than S2, then AT will equal to 1, and then 1 is not equal to 0, then I will branch, right? So overall, what I try to say is if S1 less than S2, I will branch to the instruction with label, certain given label. This is exactly equivalent to the operation try to represent it here. And if S1 larger than S2 or larger than equal to S2, then they will not branch to the instruction with certain label. Similarly here, if S1 larger or equal to S2, then AT, this general purpose register, will equal to 0, and 0 equal to 0, therefore I will not branch into the instruction with label L, with a certain given label. Then it's also satisfied what I try to represent here. You can see now I can using a set of set down less than and the branch if not equal these two official instruction to represent this pseudo instruction. Okay, now we go back to this general purpose register assembler temporary register. Why I try to using just emphasize using the word file. Why I try to represent the general purpose register using this AT, which is called the assembler temporary register. Why not using like T1 or T2 like what we do before? The reason is this assembler temporary register is preserved for this kind of translation between the pseudo instruction and the official instruction. By doing that, by preserve or reserve certain general purpose registers only for this purpose, can avoid certain confliction of the overwriting on certain registers. For example, here I will not using a assembler temporary register AT, I using T0. So in that way, basically, the assembler saw this instruction, they directly translate to here, and then using T0 as a intermediate register, and because the outside of the procedure don't know this translation, so T0 potentially is currently be used for other purpose, for example, arithmetic operation. Then when the sampler try to using T0 to do this kind of translation, they actually overwrite the value of T0 which is currently using for other purpose, for example, the other arithmetic operation. So in that will cause a confliction of the usage of certain general purpose register and will cause the potential unexpected wrong results as the output of the whole procedure. To avoid this situation, I will reserve one general purpose register only used for this translation, and this general purpose register AT will not use for any other purpose. By doing that, I can successfully avoid the overuse issue. Okay, so you suppose can borrow this similar idea or generalize a similar idea to translate those individual pseudo instructions, branch if less than equal than, branch if larger than, branch if larger equal than, to this kind of combination. So here you might has and this slide basically I try to explain this assembler temporary register. And here you might think why I only consider the equality this kind of condition as the instructions belonging to the official instruction side, and I said all the other those kind of conditional decision making operation which use the inequality condition as the judge into the pseudo instruction. The reason is, generally speaking, for the integer operation, because we know all those source operand, destination operand are integers, all those integer operation, the condition is much more likely be equality rather than inequality. Let's see more time. For the operation on the integers, the condition for making the decision is much more likely to using the equality, which represented by branch if equal, branch not equal, rather than those kind of inequality like larger than, larger equal to, and so on. And we in the future, when we try to learn the pipelining, we know the overall clock cycle of the whole system is determined by the largest or longest cycle of the certain stage of the certain instructions. Therefore, potentially, if one of the instruction is very complicated and they require much longer clock cycles, then it potentially will pull back the overall performance of overall system, even though some of the instructions require much less clock cycles compared with this clock cycle. For example, here, those instructions have much more complex condition compared with the inequality. Therefore, they will using much longer clock cycles in order to complete that operation compared with branch equal, branch not equal. If we include those less likely used or uncommon used instructions into the instruction set, then I will potentially pull back the overall performance just because of those instruction which is not that commonly used. Okay, I hope I explained that clearly. Therefore, if you recall, when the first time when we introduced those instruction and operation design, we mentioned there's one principle is we try to improve the performance of the common case. And here, branch equal, branch not equal are the common case. All the others are uncommon case. It's not reasonable to pull back or reduce the performance of the common case by only focusing on increasing the performance of the uncommon case. Therefore, we try to do the good compromise for the design. So I focus on keep the performance of the common case, and for the uncommon case, I don't mind to potentially compromise the instruction by represent this instruction by using a set, because here basically I'm using two instructions to represent same purpose. Of course, for this operation itself, the clock cycle is longer compared with if I including this instruction into the official instruction set. Okay, so here I think this will be the last concept I want to introduce in today's class. Basically, this is called the basic clock. In other words, in order to improve the overall performance, I will now focus on optimize the sequence of instructions individually. Instead, I first will classify the cluster those sequence of instructions in different blocks, and those blocks is considered as basic blocks. In other words, there's no branch in or branch out within the blocks. The whole blocks as the basic union, and then when I optimize the sequence instructions, as I said before, instead of focus on optimize the sequence of the individual instructions, I only optimize the sequence of those basic blocks. By doing that, the overall computational complexity is dramatically decreased. Let me say one more time. By focusing on reorganize or optimize the sequence of blocks, it's much simpler or require much less computational complexity compared with optimizing the individual instructions order. And at the end of today's class, I would like to do one practice. So basically, this practice help you to more familiar with the set down less than, branch if equal, branch if not equal, and those kind of sequence of instructions. So here, what I try to say is branch less than T1, 0, T0. Okay, so for this instruction, again, I want you to pause here to solve the question by yourself first, and then continue with the video. So what here is the 0 and the T0 are two source operands. I try to say whether 0 less than T0. If 0 less than T0, I will set T1 as 1, otherwise T1 will be 0. Again, the set down less than, that is a signed operation. And then I try to see whether T0 is larger than 0. So we can see here T0 as following. Some student ask me what means 0x here. 0x represent or refer the information as the T0 is represented as a hexadecimal, which means this representation is using the base of 16. Okay, so in that way we can see T0 is some positive number. Because T0 is positive number, 0 is less than T0. And because 0 less than T0, T1 will be 1. Okay, I hope it is clear to you. And then the second instruction is whether T1 and 0 are not equal. If they are not equal, I will branch to the instruction with label else. And because T1 is 1, 1 is not equal to 0, therefore I will do the branch. And then now I will skip this instruction and branch to the instruction with label else. And here what I try to do is try to do the add immediate and T1, T1, 5. Basically T1 and 5 are two source operand, and the T1 is a destination also. So T1 now is already value 1, so 1 plus 5 is equal to 6, and using that 6 to update T1. Therefore, the overall value of T1 is equal to 6. I hope it's clear, and this will end today's class. Thank you.